All right, I think we'll start it up. All right, so thank you all for joining us today for another session of the PCE3 seminar series. And if you didn't already know, PCE3 is a NASA RCN that stands for Prebiotic Chemistry and Early Earth Environments. And one of the main goals of PCE3 is to bring together researchers from various disciplines to work together towards better understanding how life may have evolved on Earth. And so one of the things we're interested in through the seminar is whether we're actually reaching this kind of a diverse audience. So one thing we wanted to do was put up a quick poll to see what everyone's interests are. So let me just bring that up right now. So that should have popped up. And so while you're all kind of working through that, I'll mention that another one of the goals of this seminar series is to highlight the work being done by early career researchers. And so today we're going to be hearing from Beth Ann Bell of UCLA and Yoshi Miyazaki from Caltech. And another note is that we're going to keep the chat closed to the questions until the end of the talks. So try to keep a note of any questions that pop up during any of the presentations. Now, before we hear from Beth Ann and Yoshi, we're going to have a short introduction for today's theme, which is Earth's early oceans and land masses. And that's going to be given by Mark Harrison of UCLA. And Mark is a distinguished professor of geochemistry at UCLA, and he's made many great contributions to our understanding of Earth's evolution. And he's been recognized for his work by receiving numerous prestigious awards, such as GSA's Day Medal and AGU's Booker Medal. So thank you for joining us today, Mark, and you can go ahead and give your presentation.
Okay, now we've had some technical hiccups here, and so Beth Ann, I think you've got my president. There we go. So we're going to do this as a tag team. Okay, look, in the absence of a rock record older than about 3.4 billion years, the prevailing view of early Earth in terms of land and oceans was essentially Harold Urey's contention that Earth had formed cold and remained so for a billion years before a segregated core mantle crust had formed. This became increasingly untenable in the early 1970s, and with the return of lunar highland rocks, showing that the moon had seemingly been completely melted on formation, the terrestrial view took a dramatic U-turn to the view that, in fact, the place was a fiery hellscape for about a billion years, and before it could cool and extensive areas of stable crust form. So this spawned a range of models shown in the next animation here that you can see. Beth Ann, can you show us where the present day and 100% of continental crust is? Okay, up there, and there we go, up in the, there we go. Getting close. Okay. And the prevailing view, next animation, is that the early crust for potentially a couple of billion years was mafic. It was basaltic, okay, low silica. And at about 2.5 billion years, if you could show that, Beth Ann, it grew rapidly to the present volume. Now you can see that there's a whole range of models here. If there is a paradigm the past 50 years, it's this view of early mafic crust, rapid continental growth 3 to 2.5 billion years ago. But recently, the foundational assumptions of the early mafic crust model has been shown to be deeply flawed. Now, that doesn't mean that the model is wrong, okay? It just means that there's no real compelling evidence to have confidence in these, in what looked like, you can see the majority of these models. This shaded region is what I would say, roughly corresponds to continental growth histories that are consistent with the evidence we have today. Okay, now, note that it's a, semi-log plot here, but what I want to drive home here is we really don't know in detail what the growth of continental crust is. Okay, now the reason we're talking about this today, next slide, is that about 20 years ago, we recognized in these little zircons, some no more than the width of one of the hairs on your head, that there's 3 lines of evidence to suggest there was water near or at the Earth's surface greater than 4 billion years ago. The first, next slide, Beth Ann, is that these inclusions, primary inclusions in this case, of minerals like biotite, hornblende, muscovite, okay? These are hydrous phases, okay? So they imply that there is water in the granite melt that formed these zircons. The next line, 20 years ago, this began to be pointed out, and Beth Ann's going to talk more about this in detail, but this is a plot of the oxygen 18 composition, how much more oxygen 18 there is than, say, the Earth or the lunar mantle. That's shown in the blue curve. Hadean zircons are offset to heavier values, and as Beth Ann will tell you, a simple way to get that result is to incorporate clays. Clays are hydrous phases, so it implies water at or near the Earth's surface. The next line of evidence, next animation, is maybe the best, and that is that when the titanium and zircon thermometer was developed 15 years ago or so, we were stunned to see the formation temperatures on the order of 700 degrees, some as low as 680, even lower. Now, the next slide shows this thermometry data together with barometry results we can get from these zircons plotted on a PT diagram showing isopleths of fraction of melt. And you can see where the Hadean zircons are forming. There's either, 0 melt or less than 3%. So if we're going to make a significant granitoid magma in this period, you're going to need water, and not a little water, maybe 50 % water or more. So you're going to need a seemingly limitless reservoir. Now, none of these 3 lines of evidence imply the existence of an ocean. And I think that this is the principal point I want to make here, is that with one exception, we really can't say that there was a global hydrosphere. And that is that these inclusions, as Beth Ann will describe, come in 2 flavors, S-type, I-type, sedimentary source, igneous source. Sedimentary type zircons, granitoids that make these zircons, have a sodium, potassium, calcium over molar aluminum ratio greater than 1. They're perluminous. And the way that we see this is happening, at least in Phanerozoic Earth, is you bring a rock to the Earth's surface, the feldspars are unhappy, they weather to clays, that releases alkalized calcium to wash into the oceans. That's why the ocean's salty. Okay? And the concentration of silicon and aluminum in the clays gets deposited on the continental shelf later to make a granite. Okay, now next slide. Now this is important because we raise Urey's name again. It's the Urey reactions, right? It's the submarine floor weathering doesn't sequester CO2 effectively compared to buoyant subaerial continents. So until we get significant subaerial rock presence, it's going to be hard to see how we're going to draw down degassed CO2 to prevent a runaway greenhouse. Next slide. But there we go. Yeah, for this virtuous cycle that keeps the surface of this planet temperate, and we don't have, say, the runaway greenhouse. So, if this is all true, then we have to do better in terms of understanding continental growth history. You saw the range of models that are consistent with existing constraints. Okay, so then next slide is summary. We are in a phase, or we're coming out of a phase where I think we got very self-satisfied about this early felsic crust rapid growth at 2.5 billion years. And it really forestalled a true understanding of continental growth history. So it's exciting now that particularly young folks listening here, that this topic is wide open. This is frontier stuff. Okay. We can talk later why the early mafic crust model is flawed. bum, 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 bum. And I think that that's really all I wanted to get across. So back to you, James.
Great. Thanks for that intro, Mark. And so next we're going to be hearing from Beth Ann Bell, who's currently an assistant project scientist in the Ion Microprobe Lab at UCLA. And Beth Ann took this position after completing a Simons collaboration on the origins of life postdoctoral fellowship. And Beth Ann's work focuses on using zircon and other igneous minerals as probes for reconstructing the Earth's earliest crust and environments. So thank you for joining us today, Beth Ann, and go ahead.
Sorry, now I'm unmuted. Thank you. Thank you very much for inviting me to give this talk. And I'm going to go over a lot of the material that Mark introduced just a few minutes ago. And first off, so we have a 4.5 billion year old planet, but we only have a rock record that has been identified back to about 4 billion years ago. So this leaves a large amount of time at the beginning of the Earth's history in which we don't have the sort of rock record where we can go out and get as definitive information as we were able to do in the more recent geologic history. And as you might imagine, this has led to a wide variety of hypotheses over the years for what the early Earth might have looked like during this formative period. So we've got two artist renditions here. One of them is remarkably less hospitable towards life and similar things than the other, as you might have guessed. And the term Hadean might seem to invoke something more like this image on the left here. When we start looking at the rock record that does exist, then we are around 3.8 billion years ago, we are able to see rocks that have been interpreted as metamorphosed marine sediments, implying something that looks much more like the artist rendition on the right here. So the question is, over what time period did the Earth go from this very high temperature, very high energy sort of environment, which if we imagine that we know something about the accretionary period of early planetary evolution, lots of meteorite impacts happening, potentially early magma oceans, at least for some period early in its history, Earth must have looked something like this. Over what time period did we go to much more clement environments? And we are increasingly able to look at the Hadean period itself before 4 billion years ago in order to get evidence for these more clement conditions happening fairly early. And as Mark told you, we are going to be relying on a mineral called zircon. So although we do not have a record of rocks, we have individual crystals of zircon, which in this case have been weathered out of their original context and are now found in a later sedimentary rock, which was deposited about 3 billion years ago. But these rocks range in age, or zircons rather, range in age back to about 4.4 billion years ago. And these are some scanning electron microscope images of zircon for comparison. So why is zircon really a very useful tool, other than the fact that it is the tool that we have from the Hadean period? Well, zircon tends to incorporate a lot of really geochemically useful species into its crystal lattice. Probably one of the most useful is uranium, which is taken up very readily by zircon, but zircon, as it's crystallizing, tends to exclude lead. And this means that zircon can be used as a very good uranium-lead geochronometer. One other virtue of zircon is that most of the geochemically interesting species that we can find in it also diffuse out very slowly. So we are able to have a very nice timestamp along with geochemical information, and they tend to be robust in zircon, except under special circumstances, through relatively high temperatures over billions of years, residence in the Earth's crust. So we have this uranium lead date that can be tied to geochemical evidence, but one potential complicating factor is that zircon, it's quite ubiquitous in many magmas that we find on the continents today and throughout Earth history. It also forms in higher temperature metamorphic settings, but it's not forming directly in the surface environment where we would expect to find prebiotic chemistry happening or the earliest biosphere on the early Earth. So how are we going to be able to use an igneous mineral to glean information about the surface environment? So when we're going to talk about the surface of the early Earth, I want want to break the lines of evidence for habitability into two different categories. So first is the solid Earth and any physical disruptions that it might present to a growing prebiotic chemistry or biosphere. And second is going to be the volatiles available in the surface environment itself. So in terms of the solid Earth, first off, how early was there a stable crust? Something that's not just going to founder on a short time scale into a magma ocean or into the mantle and fry whatever prebiotic chemistry was happening. Plate tectonics, as Mark alluded to, plays a very important role in the sort of long-term water cycle and carbon cycle on Earth today and various nutrient cycles. And also the amount of continental crust that existed at any point in Earth history is very much an open question and also very important for constraining many of these other aspects of habitability and also the nutrients that might have been available for an early biosphere. In terms of the volatiles and surface environment themselves, sort of the first order constraint is going to be the surface temperature and whether liquid water would have been available on the surface or stable there or in the near surface environment where we might expect this sort of chemistry to be taking place. Can we find evidence for water-rock interaction? And what can we say about the atmosphere itself, its composition, and so forth? So I'm going to break this into things that we can look at a bit more directly with the zircons, although since we are looking at the igneous record, we are going to still need to make some inferences. We can get some a little bit more indirect information about these other categories that I won't be talking about today. But if anybody wants to talk about them, we can talk in the Slack channel later, or you can email me for a little bit more information about how we're going to be approaching all of these questions. So first, because we are going to be using pieces of the igneous record to look at the surface environment, I want to introduce this concept of S-type and I-type granites, which Mark also introduced earlier. So we're going to get into more detail later in the talk as to what exactly these mean and how you would find clues for S-type versus I-type origins in the zircon record specifically. But briefly, I-type granites, I-type stands for igneous. So these are remelts of igneous crust. These are more common than S-type granites, and they are quite widespread on the continents. S-type granites, by contrast, are remelting of sedimentary precursors. So material that has been brought to Earth's surface and has been weathered, as Mark said, under processes where water alteration removes alkalis relative to aluminum, leaves that very aluminous material in the form of clays behind, and also leaves isotopic evidence for that water-rock interaction, which forms some of the major clues for water during the Hadean. And so we're going to get into that isotopic evidence first. And what I'm showing you here is this quantity delta O18. And for those who are not familiar with it, this stands for the ratio of the stable oxygen isotopes, oxygen 18 to oxygen 16 relative to a standard here. So the operative point of this diagram in the context we're looking at today is that rocks and minerals that are in equilibrium with the Earth's mantle come in a relatively narrow range shown in red here. And the way that you move terrestrial rocks outside of this mantle range is through aqueous alteration. So if this alteration occurs at low temperatures, you're going to tend to leave behind rock that is higher in delta O18. Higher in that oxygen 18 isotope. And an example here is low temperature weathering at Earth's surface where we produce these clays. And if this alteration occurs at higher temperatures, you tend to have rock with a lower delta O18. And this we find this in many hydrothermal environments, but I'm not really going to be talking about that today. So let's put up, this is just a compilation of Hadean zircons. And one thing that you can note is that the majority of these zircons actually are consistent with this mantle derivation. But there is a spreading of this Hadean distribution towards these higher delta O18 signatures, which is consistent with that evidence for that low temperature water rock interaction. And so let's get a little bit more time information here. So we have now delta O18 on the y-axis and age of the zircon on the x-axis. And I'm also going to, for context, show you, so in red here is the range of rocks and minerals that are in equilibrium with the Earth's mantle. And modern day S-type granites that have that big component of weathered clays are shown here in the blue field. I-type granites tend to be a little bit intermediate because many of them do assimilate a smaller amount of sediment. And so you do see some of those higher delta O18 signatures creeping in. So the earliest, also the way I have color coded this, blue means the sort of the highest quality data here. We can constrain that these analyses were collected on areas of zircons that were not cracked or altered. So the earliest one of these, where we are able to see that the zircon is resolvably higher than the mantle field, is a little over 4.3 billion years old. And you can see this substantial minority of zircons that are not consistent with the mantle, but are instead heavier in oxygen 18 than the mantle, is fairly continuous from 4.3 a billion years ago through the Hadean. So this is a quite strong signal that we're seeing. So we're seeing evidence for this heavy oxygen 18, which is evidence for low temperature water rock interaction. But can we say something about the nature of that interaction? Right now, I'm showing you a slide from Dustin Trail's work. And what we're seeing is, again, on the y-axis, delta O18. But on the x-axis is another stable isotope system, this time in the element silicon, which also responds to weathering and aqueous alteration. And so there are different pathways in these isotopic systems that a rock might take as it is altered. BSE just stands for bulk silicate earth here. Think nice, fresh, igneous rock that has not been altered yet. And so you can imagine a hydration pathway, such as might happen, say, on the ocean floor, the production of serpentinite, where that doesn't necessarily have this clay production, or this chemical weathering process that we've been talking about, where you're producing clays. So cheelite is a clay-rich rock. And so Dustin also looked at some of the Hadean Jack Hill zircons, and you can see a variety of different pathways consistent with these hydration reactions, as well as consistent with this weathering reaction and clay production. So we are seeing aqueous alteration throughout the Hadean, and potentially a variety of different styles that this might have taken. I'm going to put a pin on this for the moment and come back to it a bit later. But for right now, I want to move on to the second piece of evidence for water that Mark had talked about earlier also, and that is in titanium temperatures. So titanium is a trace element in zircon that is, it partitions into zircon. That is, you have a zircon growing in a magma, and there's titanium sort of in the magma. And the extent to which it is then found in zircon tracks so well with temperature that it can be used as a nice crystallization thermometer. Now, one caveat is that we need to understand the activity of a titanium dioxide in the magma before we are able to definitively say which temperature it is. But for a typical range of titania activities in felsic magmas, we might have to shift 50 degrees Celsius upwards or so. We assume a titanium activity of 1 for the Hadean zircons because we do find rutile inclusions in some of them, and that is titanium dioxide. So we know that for those zircons, we're having a titanium activity of 1. But anyway, what we're seeing again is these very low igneous temperatures, which compared to other environments which have been proposed as analogs for the Hadean crust, Iceland, which is this big oceanic volcanic province. And in black here, we have zircons that are grown in melt sheets formed from large meteorite impacts. These have relatively higher temperatures compared to what we're seeing in the Hadean zircons. And all of these temperatures really require a fairly large amount of dissolved water in magmas. So what I'm showing you here again, we've got temperature on the x-axis and pressure on the y-axis. And this curve here is labeled water saturated solidus. So what this basically means is lower temperature here, it's totally solid and it's partially molten above. So you can have zircon crystallizing down to the solidus, and you can see, so the more water you're putting into a magma, we've got these solid lines here are the amount of water in the magma, the lower temperatures you can keep your magma molten to and keep crystallizing those zircons. And so here is the completely anhydrous dry solidus. You can see at much higher temperatures, and increasing amounts of water are going to allow you to get to much lower temperatures. Now, the reason there's this curve here and that you're able to get to much lower temperatures at higher pressures is because higher pressures magma can dissolve more water, shown in this nice plot here. So getting to those very low temperatures that we're able to see in the Hadean zircons really requires a lot of water and probably requires somewhat higher pressures as well. So let's see what this looks like in terms of time. So again, we've got the titanium temperature on the y-axis, we've got age on the x-axis, and this is for Jack Hill zircons, which have been analyzed to date. And the average for the Hadean is shown here at a little less than 700 degrees Celsius. So most Hadean zircon is less than 750 Celsius, and in fact, the oldest dated zircon with this very low titanium signature here is a little bit younger than 4.3 billion years old. And this low temperature signature is really consistent throughout the Hadean and actually throughout the Jack Hill's zircon record. This is a very strong signal. Now, one thing I want to note here, which will become important later, is we're not seeing, there's a lot more evidence in zircons that are younger than 4.2 billion years, because the distribution of zircons, we really have a lot fewer zircons that are older than 4.2 billion years. So that's why we have a little bit scattered information older than 4.2 billion years. So I mentioned the potential uncertainties with titania activity, so we might need to shift upward by about 50 degrees Celsius. But you can see these are still temperatures that really require a lot of dissolved water. It's just not quite as unusually low temperature as we are projecting that these Hadean zircons would be. So if we can summarize what we've seen so far, there's evidence for significant amounts of dissolved water in magmas back to 4.3 billion years ago, and also evidence for these low temperature water rock interactions. So there's water in the crust dissolving into magmas in very large quantities. There's a water rock interaction occurring somewhere because we have these alteration products that have been captured in later magmas. So we have questions as to what processes the Delta 018 might be showing us. The big question here is, do these signals, they require the presence of water and interaction of water with rock, but do they require a pervasive, long-lived surface hydrosphere? Is a more intermittent hydrosphere or a more intermittent water rock interaction more consistent? And are we in fact seeing evidence for subaerial land where these weathering reactions might be taking place? So if we want to look at this more specifically, now we'll start looking more at evidence for S-type granites in particular. So we have evidence for this water, which is fairly persistent throughout the Hadean. Water rock interaction during weathering, if you'll recall, removes alkalis from the weathered rocks, leaves behind a high amount of aluminum proportionally, and gives us those nice S-type granites. So a little bit more detail on the S-type granites. What we have here is two images of sort of example S-type granites and I-type granites. So I-type granites with igneous precursors, again, are much more commonly found in the crust. They tend to be more oxidized in their chemistry, and sort of the telltale sign of this, if you're out hiking around and looking at granites, is this nice pink granite. So this is a mineral called a potassium feldspar, and it tends to dissolve a fair amount of iron 3+. So if you have an oxidized magma, you're going to have nice pink potassium feldspars. Whereas if you're looking at a white granite, all the feldspars are white, you're not really going to have that iron 3+ signature, leading to the different color. And that is more common in S-type granites because throughout much of geologic history, as we know, sediments tend to have a large component of organic matter, largely biologic remains, and that is going to lead to the more reduced chemistry of the magmas. And also, S-type granites are going to have this paraluminous signature that is a higher aluminum than the alkalis, which results from the previous weathering. And this is going to show up in the common minerals that we find in S-type granites, particularly this mineral called muscovite, which is a white mica. So for those who are not familiar, mica is one of the nice photogenic minerals that is often shown in mineralogy classes and demonstrations. You can see nice examples of it. You can see these large books of sort of sheet-like, very shiny mica. Muscovite is a white mica that is really characteristic of S-type granites in particular. So let's look at evidence for specifically S-type granites in the Hadean zircon. So what I'm showing you here, we're dimensionless on the y-axis. I'm just showing you different minerals that have shown up as inclusions trapped in these zircons. So these zircons are growing in a magma. There's other crystals floating around or trapped bits of the melt, which then crystallize. And we're going to specifically be looking at muscovite in these gray circles here. And so we have abundant muscovite actually in the Hadean zircons. It's actually one of the most abundant mineral inclusions that we find. These particular examples I'm showing you here are not associated with cracks or altered regions in the zircon, so we can be fairly certain that they are actually from the Hadean and have been preserved in their host zircon. So you can see these become quite common in the Hadean record a little earlier than 4.2 billion years ago. But again, we have that tailing off of the actual amount of zircons we have older than 4.2, so it's hard to say that they're absent beforehand. Indeed, we actually find muscovite in some of the very oldest zircons that have been found. So we have this abundant, very characteristic S-type granite mineral inclusion. We can also look at trace elements to look for evidence for the aluminosity and also the redox that is characteristic of S-type granite. So this is work by Dustin Trail, again, who is looking at aluminum in zircon as a trace element and finding that paraluminous, that is these very highly aluminous magmas tend to yield zircon with a higher aluminum contents, higher than about 4 ppm. And although they also contain some zircons that have lower contents of aluminum. So this is, again, age of Jack Hill zircons versus aluminum content. There are fields for likely metaluminous and likely paraluminous, and we're seeing this paraluminous signature even back into the Hadean, although it does become more common among some of the younger zircons at Jack Hills. So this is further evidence for the paraluminous nature of many of the magmas that formed Jack Hill zircons. Let's look at for more evidence of redox. And for this, we're going to be talking about the rare earth elements, or the lanthanides in particular. It's that little cutout section of the periodic table from lanthanum to lutetium. We're going to be looking in particular at this element cerium here. Now, the reason that geochemists really love the rare earth elements is because they are mostly found in nature in the 3+ oxidation state, and they have very systematically varying ionic radii, and this allows us to look at a lot of different geochemical processes, looking at these all as a group. But we are interested in cerium because cerium is also found in the 4+ oxidation state. And the reason that's important is because zircon really loves cerium 4+. It will gobble up any cerium 4+ it finds in the magma that it's growing from, leading to this bump up at cerium in these rare earth element patterns. And so this is going to vary with the redox state of the magma. So as you might imagine, if it's more oxidized, there's going to be a higher 4+3+ ratio. And if it's more reduced, you're going to have less cerium 4+. So here are two examples from my work. This is a highly oxidized granite from southern Nevada. You can see it's highly oxidized from the other meteorology. And there's a very, very large bump up in cerium here, very high cerium anomaly, we call it. This is a more reduced granite from Southern California. This particular granite has assimilated a fair amount of sediments, and so it has this more reduced chemistry, and it has this more muted cerium anomaly. And Dustin Trail actually calibrated the cerium anomaly as a proxy for the redox state of the magma from which the zircon grew. And there are a couple of cerium-based proxies that have grown up since Dustin published that. So what I'm showing you here is, again, age of Jack Hill zircons on the x-axis, and on the y-axis is this measure of redox. And what you need to know here is that 0 is the modern day upper mantle of the Earth, its composition. More oxidized than the mantle is positive, and less oxidized or more reduced is negative. So you would expect S-type granites to be like -2, -3 or so. I-type granites can range from the upper mantle up a couple of log units. And so again, more scattered data before 4.2 billion years in the Jack Hill zircons. But as soon as we have a lot of Jack Hill's data in the Hadean, we are seeing a wide variety of these redox states. We're seeing these highly oxidized states, which could probably tell us something about the nature of the mantle oxidation and potentially the atmosphere. If you want to talk about more about that, that is a large component of Dustin's work on this subject, as well as these more reduced signatures, a very strong reduced signature, which is much more consistent with S-type granites. And in particular, this reduced group, you start seeing it at 4.2 billion years, and it is continuous through the Hadean to at least 3.8 billion years. So this is a long-lived signature alongside that evidence for paraluminous origins as well. So what can we say? We are seeing evidence for water that's continuous through the Hadean since 4.3 billion years ago. These low temperature magmas, which require pervasive high degrees of water dissolved into them. This delta O18, which is consistent with low temperature water rock interactions throughout the Hadean. And so we want to ask, can we constrain evidence for specifically weathering and clay production and subaerial land? But we are seeing further evidence that is consistent with what we would today call S-type granites. Since at least 4.2 billion years ago, we're seeing these inclusions of highly aluminous materials, muscovite inclusions. We're seeing evidence for aluminous zircons from the aluminum contents. As Dustin has shown, we're seeing these reduced chemistries in many of the zircons since 4.2 billion years ago. And so the Jack Hill site has really given us a lot of very highly suggestive evidence, not only of long-lived water on the Hadean Earth, but also of long-lived sediment production and remelting of those sediments, probably to create S-type granites or something very like an S-type granite. However, you might ask, how representative can the Jack Hill site really be? We're trying to look at, a whole planet 4.4 billion years ago using this one site. Fortunately, there are other places on Earth where we have found Hadean zircons. So we have Jack Hills as one of these sites here in Western Australia. There are a number of others. And in many of these places, the Hadean zircons have sort of been found just through reconnaissance uranium lead surveys. There's one or a handful, but there are some notable exceptions. For example, here in the Singboom Craton, there are enough Hadean zircons that have been identified that many geochemical investigations have started happening with them. And also here in the Barberton Greenstone belt, there are also a large proportion of Hadean zircons found in a particular sediment bed here, and in particular, Nadja Draban at Harvard has been doing a lot of work to really constrain the geochemistry of these with many of the same tests that have been done on the Jack Hill zircons. And this is really going to give us a very good alternative sample set for trying to nail down what was happening on the early Earth. So I also want to briefly acknowledge my co-authors and many collaborators over the years. So my PI, Mark Harrison, many of his other graduate students, and many of our collaborators, many of whom are not mentioned here, but at other institutions, funding from the Simons Foundation and NSF. And thank you very much.
Great. Thank you, Beth Ann, for that great talk on zircons and what they can tell us about Earth's early environment. So next, we're going to be hearing from Yoshi Miyazaki, who is a Standback postdoctoral fellow at Caltech after receiving his PhD from Yale University. And Yoshi is interested in understanding the processes responsible for creating a habitable surface environment on Earth through the use of models of early stage evolution of terrestrial planets. And so thank you for joining us, Yoshi, and go ahead.
Okay, thank you. Are you seeing a screen right now?
Yeah, I think we see your wallpaper.
Okay, wait.
I think you might have muted yourself also.
Oh, okay, sorry.
Oh, there you go.
Okay, great. Are you seeing the screen now?
Yeah, it looks good.
All right, awesome. Okay, just trying to figure out how can I put out a pointer, but okay. Anyway, okay, I will start, I guess. Thank you, James, for the introduction, and thank you so much for virtually having me today. I will take a sharp turn from the observational constraints presented by Mark and Beth Ann, and we'll start to discuss what can be said about Hadean Earth from a more theoretical perspective. I used ocean formation in the title, but I will be discussing the evolution of the volatile budget in general. Because the amount of the surface volatile is mostly regulated by how much mantle ingassing and degassing took place back in Hadean, so geodynamics will also be the main focus of this talk. So as you heard from Mark and Van, there is an evidence of surface liquid water in zircon records. From a theoretical perspective though, whether liquid water was stable or not can actually be judged by a very simple criterion. And that is the amount of surface water should be larger than the amount of water vapor that can be contained in the atmosphere. It is obvious that this relationship holds for the present-day Earth. Ocean water mass is 5 orders of magnitude larger than the amount of water vapor contained in the present-day atmosphere. But whether this relationship was satisfied in the Hadean is not that obvious, and I will be discussing how the volatile amount on the Hadean surface evolved back then. The Hadean can be divided into 2 periods while Earth was in the magmotion period and a period after that when the mantle was mostly solidified. I will start off with discussing how the atmosphere evolved right after the giant impact and during the solidification of the magmotion. I will then briefly mention the interior evolution during the same period, and in the last part, I will combine 2 insights and discuss what the surface environment was like during the post-magmotion period. So to answer the first question, I'd like to go all the way back to the moon forming giant impact. The model shows that this impact melted most of the mantle and produced an ocean of magmotion all the way down to the core mantle boundary. This resets the volatile partitioning between the surface and the mantle, and differentiation during the solidification process could also be significant. So how the Earth evolved during the solidification of magmotion really sets the initial condition for the evolution of the subsequent Earth. The temperature of a magmotion could reach as high as 4,000 degrees C, and that means the convection was extremely fast in the period after. The overtime time scale, so for the magma to travel from the surface to the bottom back to the surface again, is on the order of weeks. So this is much shorter than the lifetime of a magmotion. So volatiles between the magmotion and the atmosphere was likely to be in an equilibrium state. We can predict that the amount of volatiles in the magmotion and atmosphere using the solubility to silicate magma. The right plot is one of the compilation of the experimental data. And it's a little hard to see, but I hope people are seeing my screen pointer. I'm not sure how I can do that. Anyway, but this rectangle is showing the pressure between 10 and 1,000 bar, which are expected during the magmotion period. So the blue is the water and red is the carbon dioxide. But you can see that water is much more soluble to silicate magma in this pressure range compared to the carbon dioxide. We use this solubility measurement to predict the fraction of volatiles that can be kept in the magmotion. Based on the data, we did a very simple calculation of volatile partitioning. Because the solubility increases with this, partitioning at the surface basically determines the volatile partitioning. When a total of 1 ocean mass of water was present in the magmotion hydrosphere, the majority of water would reside in the mantle, and the amount of water at the surface would only be equivalent to 7 bar. On the other hand, more than 70% of the total carbon budget could be released to the atmosphere. So the atmosphere on top of a magma ocean is likely to be extremely CO2 rich. And additionally, the gassing would obviously have
So it seems like Yoshi might be having some problems with his internet. Let me see, maybe I'll send him a quick email. And so if you guys could just hold on for 1 second, sorry about that. So while I'm doing that, I think, so Yoshi, are you back? It seems like you might have cut out for a little bit.
Yeah, I'm at my office, but somehow the internet was cut off. Let me restart these. Give me a second. Okay, I'm not sure where I got cut out, but like, are you hearing me again right now?
Yeah, we can hear you. So I think your screen is back up. So it seems your internet's good again.
Okay, great. I'm really sorry about that.
Oh, no problem. I think it's there's all things popping up during these presentations, so it's not a problem at all.
Times internet's really bad in my office. I'm not sure. Oh yeah, I think I hope you heard this part, but like let me repeat a little bit. Well, go back one slide. Okay. So I think I'm not sure when you heard till like I was on the line, but so basically what I did was like I calculated the molecular partitioning of water into carbon dioxide, and the main part is that while water is mostly kept in the mantle, carbon dioxide will be largely released to the atmosphere. And that's only the part of the story because I'm only thinking about the magma motion period in the early stage. And additional degassing would happen as magma motion solidifies from the bottom. And volatiles are incompatible elements, they concentrate the melt phase as the magma solidifies. But it doesn't really mean that all the volatiles would degas when magma
So it looks like maybe he might have cut off again. So let's see. Oh, I see that he's back. Are you?
not sure what's going on. Sorry, I've never had this issue in my office.
Yeah, I was thinking maybe. Yeah, is that? Yeah, it's pulling up again. So
Yeah.
I think
Okay.
one thing that people have done is if you turn off your video, it sometimes can help. So maybe if you turn your video off and just do audio, that might help.
I need to see my face. So.
Or yeah, turn your camera off. Yeah.
Yeah. So additional degassing would happen as the magma motion solidifies, but it doesn't mean that it will, all the volatiles will be released to the atmosphere. To understand how much of it actually degasses, I'll briefly mention the sequence of a magma motion solidification. And the word magma motion is actually a bit confusing because it implies an ocean of liquid like magma. But as magma motion cools down, crystals start to interconnect, and the magma layer would actually turn into a very mushy state. The transition happens from the bottom to the top as melt fraction reaches 40%, and the viscosity would increase by orders of magnitude as this transition happens. The rheology will become similar to the present current mantle, but yet trapping a significant amount of partial melt. This partial melt could include a concentrated level of volatiles, but because they exist in pore space in the solid matrix, the volatiles may never be released to the atmosphere. The process that could actually release the volatiles out of the solid layer is melt percolation. Imagine squeezing water out of a cleaning sponge, but instead of your hand pushing the water out, the density difference between the solid and the liquid will be driving the flow. The efficiency of percolation, however, is highly uncertain because it depends on the square of grain size of solid matrix, which we don't have a great understanding on. On top of that, the Rayleigh-Taylor instability within the solid state layer would transport the layer with partial melt downwards, which would sequester volatiles in the deep mantle. These are examples of volatile degassing calculations during magma motion solidification. The left model assumes some level of volatile release by compaction, while the right is from my paper this year, assuming compaction is very inefficient. In this right case, volatile is mostly kept in the solid state layer, but the results differ depending on the models. But two things are robust over here. One, more than 90% of total carbon dioxide budget would be released to the atmosphere. And two, on the other hand, like the significant fraction of water will be kept in the mantle. In a scenario that volatile release was inefficient by compaction, more than 90% of the water budget could reside in the interior instead of the atmosphere at the time of magma motion solidification. So what does this tell us? With the volatile concentration I used in the earlier slides, around like 5 times 10 to the 19 kilograms would be released to the surface, assuming this is a warm water mass was present in the hydrosphere in the magma ocean. Because a huge amount of greenhouse gas is released, the amount of water vapor in the atmosphere can be 3 orders of magnitude larger than the present day. So surface water mass here is still larger than the amount of water vapor than the atmosphere can hold. So liquid water should have been stable on the Earth's surface, but there may not have been enough water to create something like an ocean right after the magma ocean solidification. And the bigger problem here is the existence of like massive CO2 atmosphere. Even we assume a moderate like CO2 concentration in the mantle at that point, the estimates, the atmospheric pressure of CO2 would exceed like at least hundreds of bars. But the estimates of CO2 for global carbon cycle or various estimates during the Archean show that CO2 pressure in the late Hadean and early Archean period should have been likely on the order of 0.1 or 1 bar. This is obviously higher than now, but still not at the level of creating an extreme surface environment with a steamy atmosphere. So there should have been a dramatic drop in atmospheric CO2 level within just a few hundred million years, and how that could have happen is like the focus of the rest of my talk. The problem of need to remove a huge amount of CO2 was originally realized by Kevin Zanley and Norm Sleep, and their solution to this problem was that tectonics was really active in the Hadean, and they wrote in one of their review papers that the lower viscosity let foundering crustal blocks sink more quickly. If the seafloor was renewed very rapidly, carbon could have an efficient sequester to the mantle by subduction, and active tectonics in the early Earth actually do seem intuitive. And we can point to some geochemical data to support that. This is just an example, but like 142 neodymium isotope data has been suggested to indicate an efficient crustal recycling during the Hadean period. But the general belief that a hotter mantle convects faster because of a lower viscosity is not necessarily supported by like all lines of geological data. The left top plot is the thermal history of Earth on top of the petrological estimates. The temperature decrease, if you can see like the circles here and the line, the temperature decrease was actually slower in the past. So 0 is the present and 4 as you go the way back. So you can see the lines lying down in the 3 and 4 period. And this could also be seen as so they were actually slower in the past, and that means convection should have been much more sluggish. The right figure shows the number of zircon samples, and the peak can be correlated with the formation of supercontinents. The longer supercontinent cycle means that time it needed to bring together the continent was actually longer. So this could also be such an indication of a slower plate motion under a hotter mantle. That can be counterintuitive because hotter mantle has a lower viscosity, and the reason for this explanation is the melting below mid-ocean ridges can actually play a role in it, and this is posed by my PhD advisor, John Kurnaga. The partial melting of the mantle becomes the source for a basaltic crust, but it also leaves a depleted lithosphere, which is dry because of a melt extraction. Dry out, oops, it says internet unstable. I hope it's connected. Okay, dry olivine has a viscosity higher by a factor of 100 or maybe 1,000. So under a hotter mantle, more melt will be generated, so the depleted lithosphere becomes thicker. In that case, subduction becomes harder because dry lithosphere has a higher viscosity than the ambient mantle. If we consider the presence of a thick and stiff depleted lithosphere, we can actually naturally explain the slower plate velocity under a hotter mantle. This is a figure that shows a quantification of the thickness of crust, depleted lithosphere, and we also calculate the plate velocity using heat flow scaling. The estimated thickness of crust in the depleted lithosphere is going to grow under a hotter mantle, and with a temperature higher by 300 Kelvin, the thickness of depleted lithosphere would grow nearly 3 times the present day value. Also, plate becomes more buoyant, so it needs more time for plate to cool down and become heavier than the ambient mantle. With these two effects combined, the plate motion in the Hadean is predicted to be similar to the present day, or even under a hotter mantle. So if we use that value of like 5 centibar per year for the plate velocity, how long would it take to say like remove 200 bar of CO2? if all magnesium and calcium silicate were used to form carbonates at the seafloor, let me assume I'm maybe using a quotation of fuck here.
You look. Are you there, Yoshi?
Yeah, I'm here.
Oh, sorry.
I'm, I'm really sorry.
No problem. There's always some kind of technical difficulties with that.
The weird thing is like I don't see this. Are you seeing my screen right now or?
Right now we're seeing now we see your slides.
Okay. Okay.
Yeah.
So, oh yeah, I'm using the quotation because like it's not necessary the case that like something like a ocean existed at that point. But assuming that there's some amount of liquid water there, and if all magnesium and calcium silicate were used there to form carbonates, the seafloor would hold roughly like 10 bars of CO2 at the time, one time. But still, that means the seafloor has to be renewed every 20 times. And if you use the present day renewal value of 90 million years, it could take 1.8 billion years to remove all CO2. And this is a very optimistic calculation, and the actual number should be much larger. We are assuming that carbonates don't melt or decompose during subduction, and the amount of CO2 stored at the seafloor could be smaller than 10 bars in reality. And also, with a smaller surface liquid water mass at that point, drawdown or weathering could be inefficient as well. So was the surface in an extreme greenhouse state until the late Archean or even until early Proterozoic? That seems very unlikely for given the geological data we have. And we can revisit one of the assumptions we're making so far. That is that the Hadean mantle had the same paralitic composition as a present-day mantle. But magma ocean could have differentiated the mantle significantly during the solidification process, and the mantles might have been highly heterogeneous at that time. So I will take a brief detour from the volatile budget and briefly discuss the differentiation process during the magma ocean. There are two mechanisms that can drive the differentiation, and the first one happens during the earlier period when magma is behaving as liquids. It's a very shitty cartoon, but as the magma ocean cools down, a small amount of crystals start to coagulate. And in general, crystals are heavier than the rest of the magma. So they can settle down and accumulate at the bottom of the mantle and accumulate in the bottom of the mantle. So in a magma ocean, magnesium is partitioned more into crystals. So this crystal accumulated layer will have a higher Mg number, whereas the rest of the liquid will be more depleted in magnesium and enriched in iron. The other process that could drive the differentiation, the compaction of the solid matrix, and it also has a similar effect. It's the same thing as when I discussed the release of volatiles from the solid state layer by squeezing like the sponge. The layer dominated by crystals would trap some amount of melt in the pore space, and these melt are more enriched in iron. So if you squeeze this melt out, this solid layer is going to be depleted in iron, and more enriched in iron, whereas the liquid layer becomes more enriched in iron. For the sake of time, I will skip the details, but as my magma ocean solidifies from the bottom, high Mg number solid layer would grow, and whereas the remaining liquid will be more enriched in iron. And once this solidifies, this structure is gravitationally unstable because you see the surface layer is more enriched in iron, which would cause the layer to be more heavy. And so that would result in the downward transport of iron-rich materials. And I did a simple analysis of the length scale and time scale and stability to see how the structure would evolve after the magma ocean solidifies. This dispersion relationship suggests that most unstable mode has a wavelength shorter than 100 kilometers, so instability will most likely show a dripping-like behavior. Because of the high solid viscosity, iron drips may not be completely homogenized and could rather continue to exist as small blobs or some transported all the way to the core mantle boundary. As you can see in the schematic diagrams, the onset of short-length scale instability likely creates a small iron-rich blobs embedded in the high Mg number matrix. Now, with that in mind, I would like to go back to the question of how a massive CO2 atmosphere could be removed in such a short amount of time. And the key is in the heterogeneous nature of the mantle. When the mantle is differentiated and is made of two components, minerals with low melting temperature, like plagioclase or CPX, are mostly concentrated in the iron-rich reservoir side. So the remaining high mg number matrix has a much higher solidus than the original pyrolytic mantle. Here I calculated the phase diagram of two components using the MELTS program. Contours show the melt fraction, and the gray line represents the adiabat of 1600 degrees C, like a rough estimate of the Hadean mantle temperature. A pyrolite starts to melt at like around 5 GPa under this temperature, but with a high mg number matrix, it won't melt until 2.5 GPa. Obviously, this iron-rich reservoirs probably existing as blobs would melt deeper down, but because they exist as small blobs, it won't create a uniformly thick dry lithosphere. So this is the picture we suggest for the surface structure of the heterogeneous mantle. High mg number matrix melts at 2.5 GPa and form a high mg number crust and depleted lithospheric mantle. Iron-rich reservoir would most exist as small blobs, most likely exist as small blobs, and they will melt at a deeper depth, but it only melts locally and will not dehydrate the entire near surface region. So the heterogeneous mantle lacks a thick crust, as in the last shown in a pyrolytic mantle, so plate velocity could be faster than the case of a than the case of a pyrolytic mantle. Again, we quantify the thickness of crust, depleted lithosphere, and plate velocity. We calculate the crustal thickness using the phase diagram I showed in the earlier slides, and the thickness of you can see here that the thickness of the depleted lithosphere decreases by a factor of 4. The black line is the original pyrolytic mantle, and the red one was the case if it's heterogeneous. So unlike the pyrolytic mantle, the plate velocity won't be limited by a thick, dry, and stiff layer anymore. So even at a higher potential mantle temperature, plate velocity won't be limited and could be as fast as 50 centimeter per year. This is roughly 10 times faster than a pyrolytic mantle. And so the speed of carbon sequestration would be very different if the mantle was heterogeneous as a result of magma ocean differentiation. If the mantle was heterogeneous, the dry and stiff layer will be thin, so the surface could be renewed every 10 million years. And on top of that, a higher mantle temperature results in more olivine and OPX content in oceanic crust, so the crust could have a lot more capacity to store and form carbonates. With these two effects combined, the surface temperature can drop to the modern level in nearly 150 million years. Obviously, this is a little optimistic case, but the left figure shows the evolution of atmospheric pressure and the right is the surface temperature. But even if it's an optimistic case and actually factor too longer, it is still pretty likely that a climate surface environment emerged by the end of the Hadean. On the other hand, for a pyrolytic mantle, the slow post-plate motion would limit the speed of carbonate reduction. So, and given that the surface is only being renewed only 90 million years, it takes nearly 2 billion years to draw down a massive amount, like 200 bar of CO2. Again, we're assuming that all carbonates are delivered to the mantle. So in reality, this time scale should be much longer. With a pyrolytic mantle, it predicts that late Archean still had a surface temperature of 200 higher than 200 degrees C, and that is probably not the case. So what I'm doing here is like to connecting the studies of magma ocean and Archean, which can often be studied separately. And magma ocean studies in particular have lacked theoretical constraints, but we may be able to place a new constraints over here by looking at what's happening during the Hadean period. So here's the scenario I proposed for the Hadean surface environment evolution. After the giant impact, a huge amount of CO2 was released to the atmosphere, which is pretty robust, while the water would remain in the mantle. That's problematic as we don't see that kind of CO2 atmosphere now, but the heterogeneous nature of the mantle would have allowed for rapid plate motion, and that resulted in an efficient carbon sequestration. That would result in a weaker greenhouse effect, and the atmosphere would contain much less water vapor. And on top of that, active tectonics would allow for efficient degassing of water as well. So it may not be supported by Zircon so far, but we would expect to see a growing water oceans during the Hadean period. And the heterogeneous nature of the mantle will be gradually homogenized by vigorous convection, and will become closer to pyrolite as time goes on. I didn't mention much about the crustal formation in this talk, but rapid tectonics would also allow for melting during the subduction process and formation of a felsic crust. That's really the main part of my talk, but I would like to add 2 comments, as this is the PCE thermometer as for the implication of our model. I didn't really focus on the iron-rich blobs that's emerged during the as a result of magma ocean differentiation, but the melting of blobs would also create a localized crust, and it's expected to have a higher olivine content. And like, for example, marble only contains about 10% olivine, but iron-rich crust would contain nearly 40%. And olivine is easily serpentinized when it reacts with water. So the reaction between water and olivine may be occurring globally on the Haitian seafloor. And most importantly, this olivine is rich in iron, so the serpentinization of phthalate releases hydrogen and methane to the atmosphere. And this resembles what is seen in the Lost City hydrothermal field, where methane is released by seafloor serpentinization. And indeed, microorganisms that use reduced compound as chemical energy are known to create biological communities there. So the chemically heterogeneous mantle may not only remove the CO2 from the atmosphere, but it could also be a key to providing a perfect environment for the earthly life to grow. The other implication I want to mention is about Venus. So I would like to go all the way back to the first slide, the equation I showed, that is the surface water has to be larger than atmospheric water vapor content. But I mentioned that this equation likely holds for the case of Earth, and even in a very inefficient degassing case. But the amount of water vapor that can be contained in the atmosphere increases by roughly a factor of 2 for Venus because it receives a stronger radiation. So it's possible that Venus' surface weren't able to stabilize any liquid water. And the presence of surface water, liquid water, has been suggested to be important for plate tectonics. And if, for the sake of argument, we assume that without water, plate tectonics doesn't operate on Venus, that means there is no subduction of carbon, and the thick atmosphere of CO2 would be sustained for a very long time, and probably until now, as we see right now. So if Venus never had plate tectonics, the speed of degassing would be slow, and water could readily escape to space as it gets degassed. So this could suggest that water oceans have never emerged on the surface of Venus. And this could really explain why the 2 planets has a divergent path of evolution. That's it for my talk. Then this work was mostly from my PhD thesis at Yale, but there was significant change during the review process after I got to Caltech. So I'd like to thank all the funding sources during the past few years, and especially, and also to my PhD advisor, Jun Kurnaga. I thank everyone for listening, and please let me know if you have any questions. But last of all, I'm really sorry about the internet connection. It never happened before, but fortunately, it was really bad today.
Great. Thanks, Yoshi. And yeah, definitely don't worry about the internet. Everyone has issues. It's nothing you can control. I think everyone was able to get your message. So yeah, thanks again for that. And yeah, so now that everyone's had a chance to go ahead and talk, we're gonna open it up to questions. So yeah, you can type it into the chat, or you can also raise your hand in this using this I guess it's the reactions button in Zoom. So I see that Kevin Devine has raised his hand, so I think you should be able to unmute.
Okay, yes. Thanks, guys, for 2 very intriguing talks. I enjoyed the both of them. It's a bit outside my field of expertise, but I've got a question for Yoshi, and I like the fact you compared the early Earth, what we know about it, with the early Venus. And one significant difference between the 2 planets, which stands out, I think, is the fact that the moon formation event. We have a relatively large moon, and at that time, between 4.5 and 4 billion years ago, it would have been closer to the Earth, and it would have exerted a much more powerful gravitational attraction. I think, is that also essential to plate tectonics and the sort of mantle dynamics? That's something that, as far as we know, Venus never had. And could that also be a significant factor as to why the 2 planets evolved so differently?
This is a great question, and thanks. So the I'm not sure about the efficiency of plate tectonics itself, but the one key factor is obviously the tidal heating that especially when the moon was driving away from the Earth and during that period, and that would present a huge amount of heat back into the Earth's interior. And with that, there could be a prolonged time of partial melt region, and it would allow for more time for melt to escape from the interior down up to the surface. And together with the percolation of melt, it would release some volatiles. So the amount of volatiles that they release during that period should also be large, but which doesn't really happen for Venus. So again, like the amount of volatiles and especially water in Venus could be limited because of that as well.
Mm-hmm. And also the fact that, you know, when the impact happened, you'd have had a lot of molten iron and other metals which will react with CO2. So how does that, I mean, I presume that would produce a lot of methane, and that'd be methane, probably formaldehyde and other intermediates between methane and CO2. So that's something else that didn't happen with Venus, as far as we know. You know, I mean, they're the two things that stand out for me. I mean, I personally think in order to have a planet like ours that keeps going, that keeps maintaining a nice disequilibrium, we need a relatively large moon, something Mars doesn't have either, which is why conditions after about maybe 1.5 to 2 billion years, conditions basically when the core stopped moving, the magnetic field stopped, and then eventually the thicker atmosphere was eventually eroded by the solar winds.
Okay, I was having a connection problem again, but yes, I guess those factors obviously. I think there's a lot of things that I didn't really mention is obviously the impact flux, and that would also bring some sort of a iron reduced island at the surface, and that can change the volatile budget as well, and also the thermal history, which could lead to like the dynamo formation. So those things I haven't really talked about, and personally I haven't thought about yet. But obviously, that would play key roles in the different evolutionary path of the planets.
Okay, I see in the chat there was a question from I guess Bill McKinnon, and I think it's for Yoshi. And I think it's,
okay.
do you see that
Actually,
one about,
for that one, actually, I had a right axis, a different one. For H2 was in a millibar, so it's on the order of like 0.1 bar. But still large. But I think we do expect to see those escape as you mentioned.
Okay, great. And I see that the next question, it looks like it was also for you, Yoshi, and it's asking, does the serpentinization process mean that more iron 3+ will be available on radiant Earth? And what would this imply for the iron 2+ to iron 3+ ratio?
Yeah, I would say that some suggest that the kind of magma ocean modeling is there are a lot of models. Some say that it will never show up to the surface, but like if it's true that it was readily available at the surface because it was small scale, and it becomes serpentinized, I do think that would produce more iron 3+ available, and yes, so I think that would mean like the oxide condition was produced during that period, but in the mantle side, but at the same time, it would release the hydrogen to the surface. So how that interacted is I'm not sure that's really obvious for me right now, and I have to think about it. But at least for the mantle side, it may have kept created in some sort of oxidized condition.
Okay, so I see that there was another question from Richard, and I think Beth Ann might have some inputs on this from some of her earlier work on zircons, and he's asking about the lower bound for when life on Earth could have started.
Yeah, so I think that's from the zircon evidence. I mean, we can say that there is evidence for water back to about 4.3 billion years ago. So whatever form it would have been in, and so that might be an estimate, but we don't have larger degrees of evidence for that. We do have we do have more evidence for S-type granites, which is, in my opinion, more suggestive of these sort of bodies of water and land environment as early as 4.2 billion years ago. So potentially you could say that, but I think it's hard to put a really hard and fast estimate on it. But that from the Zircon perspective, I don't know if Mark, if you would also have different thoughts.
I'd ask you, do you know of any evidence that precludes life existing at 4.45 billion years?
No.
Well, like if you are concerned about some sort of surface temperature condition, I would say it takes at least like 100 or 200 million years for like if the life requires something similar to the present day temperature. But that's some sort of like a lower, like, it could be longer, but that's my perspective.
Yeah, maybe the early life doesn't know about your model.
No, definitely not. I'm just saying about like the temperature, and that's all I can say right now. I'm a physicist, so.
So I had a question, I guess, for Beth Ann. And I think one of the things that people are interested in, like as you were talking about, is perhaps the amount of water relative to the amount of subaerial land early in Earth history. And it looks like you were maybe pointing out that you're starting to find these really old zircons in different regions besides Jack Hills. So I guess if you start looking at evidence for water in different locations, does that give you more of an idea on perhaps spatial spatial restrictions of where water was on early Earth, or is that really not applicable?
Well, I mean, even on our planet today, you can find some igneous products that don't have the really aqueous signature to them, that aren't S-type granites, that are more just straight melts of the mantle. Although, many of those are more mafic and are less likely to have zircon in them. So I would say if other Hadean zircon populations are not seeing evidence for water, it's not necessarily showing that water was not widespread around the Earth's surface, but it does make the Jack Hill zircons more curious that they do have this very strong aqueous signal. Whereas but of course, if you compare it to the diversity of igneous environments on the Earth today, I'm not sure. Going from the zircon record to an estimate for the volumes of water and dry land, I'm not entirely sure. I think I need to think more about that.
Great, thanks. So let's see. At the moment, I'm not really seeing any more questions in the chat or from any raised hands, so maybe I'll just take a few seconds to thank the speakers, and if anything pops up in the chat, I'll go ahead and ask that. But thank you to Beth Ann, Mark, and Yoshi today for coming and giving these great talks, and we really appreciate it. And if we don't see any more questions, I think maybe we'll end the session here. So thanks again.
Thanks, James.